Okay, I want to welcome everyone back from lunch. I am Amber Blunt. I'm former president, or past president for TAG, manager of a groundwater district in West Texas, part of the planning committee, which gets you voluntold to facilitate things in the afternoon. So here I am. So first of all, we want to thank you to North Texas GCD for providing lunch for us all. We're going to try not to waste time, so to keep everything on track, we will have questions afterwards, but I'm not going to do the full bios. If you could just look in your programs for those. And then if time permits, we'll get to questions, because I know people like to jump back and forth between breakouts, so we'll try to get the questions with the presenters right after. But we're going to start with Brent Elliott. He is an associate research professor for BEG, and his title is Critical Minerals in Produced Water. So thank you, Brent.
All right, and so the title was Critical Elements in Produced Water, but you can see from the title here on the slide that lithium and oilfield waters in Texas kind of really should be the story, because that's what I'm going to present here. Lithium is the story for produced waters. It's about the only one that we've been able to analyze that's inside these as an economically viable resource. And so I'll kind of describe that. I do have some geochemistry that I'll show, kind of the rest of the geochemistry. But so the other people who are involved in this project are Roxana Davari, who is at the BEG, JP Nico, Bridget Scanlon, Rich Kyle, all have had some kind of contribution to some parts of this research over the past 5 years. I'll try to move fairly quickly because I have a lot of slides and I don't want to go over time. So the question is kind of, why is the urgency? Why do we need to find all of these critical minerals or critical elements? Most people probably have some kind of familiarity with this critical minerals list that was put out by the Department of Energy and the USGS. We need to find some kind of domestic supply. And then the whole push for this typically has been for microelectronics, right? The future technologies, as well as an energy transition that's kind of been pushed by our legislation, the bipartisan infrastructure legislation or law, the Infrastructure Investment and Jobs Act. All of these are kind of focused on moving to a low carbon future for energy generation, as well as funding that goes through the Department of Interior, things like EMRI, or the Earth Mineral Resource Initiative, or NGG DPP is another funding initiative for the National Geological and Geophysical Data Preservation Project, which is kind of a mouthful. The Department of Energy, Core CM, the Carbon Ore, Rare Earth, and Critical Minerals kind of initiative that's kind of pushing into different technology readiness levels currently, as well as funding more kind of characterization and assessment for various resources around the U.S. And the USGS minerals program has been funded as well. And they're pushing a lot of that money down into research organizations and industry partners in order to facilitate that energy transition. So there's also a number of announced pledge scenarios, right, or the APS, net zero emissions, right? If we want to get to a certain level of renewable energy or low carbon alternatives for energy generation, then those are the numbers that they've kind of set as those targets out into the future, 2030, 2040, extending out that far, or at least that near future. In order to meet those, we have to find those resources or have them available in order to meet those goals. And so there's a very large list here. I guess I should say that criticality is one aspect of it. Scarcity doesn't necessarily play into this, because we do know where a bunch of these critical elements are, right? We know how to get them out of the ground and process them, but there's a lot of impediments to making that happen. So as far as their importance to energy, the near term, or the short term, that's now, between 2020 and 2025 when the DOE put this out. Lithium and uranium, for example, were at the top of the list, but not quite critical yet. And so next year, kind of moving over into the critical field, lithium, nickel, cobalt, graphite, a lot of the rare earth elements, manufacturing capabilities for renewable energy sources, things like solar and wind generation, require a lot of these specific materials or elements. So if we look at the market value, in 2023, it was about $350 billion in US dollars. We look at the far left-hand side there. In order to meet those pledge scenarios or the net zero emissions in the next 15 years, you can see that the valuation for that mineral material is gonna about double, right? More than double. It's going to be more than $750 billion in revenue generated from just these elements alone: cobalt, copper, graphite, lithium, nickel, and the rare earths. Those being the critical ones that have the kind of the highest risk. That's also on that right-hand chart there. You can see lithium and graphite because of electric vehicle goals and battery storage capacity, manufacturing of both solar and wind generating materials. Right, all of those are going to have some kind of risk associated with it, whether it's supply, whether or not it's available. You have geopolitical risks where we have maybe some kind of unrest in an area that may impact supply. You have things like secondary sources that aren't available, and so you may have supply disruptions or inability to get that material. I think we saw a lot of that back in 2020, and you saw the supply chain was affected in a serious way. And so there's fears, right? There's a risk of some of these materials not being able to get to market if some scenario like that happens again. And of course, there's other factors like social or environmental or climate risks that may be associated with one or more of these commodities. So I'll kind of go through these fairly fast. All of this information, and the EIA has a list of these critical minerals, and a lot of this data can be found there on their websites. So copper is on that list, but it's not really a factor of supply currently. Right, the fear, though, is that we're going to have copper supply dwindling over time with our current mining of it. And a lot of it is being processed in China, so that has an inherent risk when you have it refined in a non-domestic way. So we see that supply over on the far right-hand side, the lower right-hand side, you see the net zero emission and those pledge scenarios, kind of relatively flat, but supply dwindling through 2040. Nickel has a bigger factor with where it's being produced and where it's being refined. Indonesia kind of controls both of those. And so if we rely on an international supply, then we don't have a domestic supply, and that carries a lot of risk with it as well. But it's relatively flat production over time, unless we find some new materials, at least on the domestic side. Cobalt, you can see inside the mining requirements for it, it's in kind of the kiloton scale, so it's, we require less, but with dwindling supply, and with most of it being produced in the Congo or being refined in China, those make it really hard for us to get to if we need it in short order. Graphite, or this is a carbon material. Graphite has in high demand if we're going to make a lot of electric vehicles, or we're going to have a battery storage capacity, and then we really need to have graphite there to make that anode material in our batteries. So most of that production is in China, and 93% of that refining capacity is in China. So that makes it really difficult if we have international relations that aren't the best at times. And they control both the production and the refining capacity. They basically control the market and the price. There are a number of projects that have been announced. There's a very large project for graphite over in Alaska that's being kind of ramped up currently. And so there are a number of these resources that we've found domestically, and we've known they've been there for a long time, but I think a lot more research and a lot more exploration is going into it now for graphite. Right, rare earth elements, we don't need a whole lot of it, but China pretty much, again, controls production and refining capacity. And so they control the price of the market. And so if we're out exploring for it now, there was a time not too far in the past where the price for the rare earth elements were really high, and so a lot of the exploration ramped up, and then China dumped a bunch of rare earth elements onto the market and dropped the price. And so there's a real risk there for businesses if they really want to get into the rare earth game. Then there's an inherent risk there because the market may crash on them. So it makes people hesitant to get into it without some kind of backing. So lithium is one of the kind of outliers for all these risk scenarios. And you see that the supply doesn't really increase that much, but our net zero emission goals and our pledge scenario goals are increasing that gap between supply and demand over the next 15 years. All right, China, again, has most of the refining capacity, but the sourcing of that material is kind of distributed between Australia, Chile, and China. And there's a number of projects that have developed across the U.S. to look for domestic supply and really ramp that up, given all the different funding sources that are out there now. So where does lithium come from? Typically, most of our lithium's from our closed basin brines in South America. Chile, Argentina, and Bolivia, for example, produce majority of that lithium material. Kind of secondary sources of pegmatites, think Australia, South America, from Brazil. As far as that material, China has a lot of the closed basin brines as well as pegmatites. You can see the United States is kind of behind those in what we have available to us, but it's a bigger distribution of source material. You get it from clay material from some of these projects out in the West, from clay deposits or from near surface brines. We have pegmatites and pegmatite projects that are being developed in like North Carolina and Appalachia or Southern Appalachia in the Piedmont area, as well as over in Idaho. Or we may have some of the deep brines or formational brine material that's coming from our oil and gas basins. So an example of kind of the footprint you may see from like Clayton Valley, Nevada, and the kind of the ppm or milligrams per liter range of concentration, about 160 ppm. You can see that the scale of difference in concentration from a hard rock mining operation, 6% or 60,000 ppm. But both the environmental and social issues that come along with hard rock mining, as well as the length of time it takes to permit, those are all impediments or obstacles to the development of new resources. And look over our majority of our supply that comes from South America. That's that kind of bottom right-hand picture in the salars and kind of the high desert areas in South America, around 1,400 ppm and the concentration. And then our oil and gas brines, which we're talking about now, and I'll kind of go through a lot of the data from Texas, but we're seeing a lot more exploration, seeing a lot more analysis that's coming forth in order to extract it or take advantage of it as a resource that already has an infrastructure that's built and developed in order to produce that water. So it seems like a pretty natural transition for some of the oil and gas wells that are that may be coming to the end of their time frame, marginal wells that are no longer effective, but they do produce a lot of water. So just as a correlation chart across the geochemistry from a lot of the averages of samples, you can see lithium up there in the top left-hand or the top part of the chart. It correlates with a lot of the TDS or major elements that form a lot of the salts in these brines, but it doesn't really correlate well with much else in terms of rare earth or critical mineral potential in most of the brines. So that's why I've kind of transitioned from a critical element focus to just lithium, because lithium is the critical element that's available to us inside these waters. So if you look at the oil and gas basins across the United States, there's a lot of potential. The Bakken up in North Dakota in the Williston Basin, that's one area that's being explored for some of these oil field brines, naturally because of the production that's already there. It's easy to go out and grab a sample off either a separator or a water disposal. Same thing with the Marcellus Shale over in the Appalachian area. They have some promising values in those areas. Of course, we're concentrating on all of the material here in Texas as part of the BEG's mandate, as the Geological Survey, to go out and kind of analyze all of either the oil, the rock, the water, as we can, and working with a lot of operators to take those samples and build a geochemical database and try to understand the potential for resources in these areas. So a lot of the data was taken from the USGS Produced Water Database, and that was updated recently. So there's a lot of good data in there. It's not all consistent as far as the chemical or the analytical equipment that analyzed it. And so it's you have to kind of pick through that data and kind of look at what makes sense or what doesn't make sense in it. It's there for the taking through the USGS, but it really has to be evaluated kind of independently. We have a lot of samples at the Bureau that haven't been analyzed that were collected back in the 50s to the 60s. You can see kind of the distribution chart there of where those samples were collected and historically, and then more recently, where we went out and kind of tried to get it with operators and collect directly from the production out in, say, the Permian Basin, for example, or the Eagle Ford Trend, or Barnett, or one of the other oil and gas basins here in Texas. So we had about 900 archive samples that we're still going through and analyzing and going out and collecting more on a regular basis. So for major, minor, and trace elements. So this study that we've done for lithium in produced water, these brines in Texas, we analyzed almost 2,500 samples from data from everywhere from the Smackover because of the high interest, but we try to get a good assortment of samples from across the entire state. The Permian, of course, we have a lot of data from the Permian just because of the activity that was happening there. We have some legacy data from the Barnett in North Texas and from the Granite Wash area in the Anadarko Basin in the Panhandle. But those areas that are currently producing or currently hot as far as oil and gas goes, those are ones that are more likely targets for sampling now and in the future, just because of the availability. You can see on average for the frequency chart there that of all the samples that we are able to analyze, the average value is probably about 14 parts per million there in the center of that graph. We have some values that extend all the way out into more than 1,000 or closer to 1,400 ppm on the very far end, but those are very far and few and far between as far as the samples go. So the interest in the Smackover is pretty strong. We see a lot of lease acres being taken up. I think if you've followed the news, Exxon bought up a large position, thousands of acres there. I've talked to a number of companies have locked up thousands of acres, particularly just for brine mining in the future, not for the marginal well capacity of the Smackover wells. So back in March of 2023, Standard Lithium had come out from an East Texas well that was 650 plus ppm of lithium. And then more recently in October of 23, they probably have more data now, but over 800 ppm for one of those wells that they were looking at. So the values has been kind of, I wouldn't say random necessarily. There's a wide distribution, a wide range of those values for lithium from the Smackover, depending on where you're at. In Arkansas, Louisiana, Mississippi, or Texas, or even in Texas, there's a wide range. So there are hot spots that we're trying to tease out now, given the amount of data that we have. We have limited amount so far. And now it's even more harder because everybody's out exploring for it and then trying to get access to those samples and report on them. It created a boom, in a sense, for getting those samples or access to those samples. So we kind of look at the distribution of concentrations and various types of source materials. Those dark triangles across the top of the chart are pegmatites or hard rock mining sources, and typically in the thousands of ppm range. The red diamond symbols are kind of represent those salars, the South American surface brines that we get most of our material from. I think it's hard to see the Smackover one on the far right-hand side, but the Smackover is kind of one of those dark squares. And it kind of reaches the bottom end. At least when this was analyzed, it was at the lower end of what a South American brine would look like in terms of composition, before a lot of the analysis that have been done have come to light. So in Texas, this is kind of a snapshot, and this is from a paper we put out I think it was earlier this year, where Darvari et al., I think it's in the Journal of Petroleum Exploration. So you can see the symbols, the bigger the symbol, the higher the lithium concentration from those analyses. And you can see a very high concentration of those high values over in Arkansas, in southern Arkansas, in the Smackover, where the historic bromine mining operations are. And so there's a big interest in putting in a lithium line for those same operations, where most of the acreage is being bought up through southern Arkansas into northern Louisiana and off into Texas. But of kind of interest and note, the Anadarko Basin and the Granite Wash there in the Panhandle also has a number of high values that have been reported, as well as in South Texas in the Eagle Ford Trend, south of the San Marcos Arch, closer to the Corpus Christi and Bama area relative to the other areas in the Eagle Ford Trend. And also probably to note is that, the Permian Basin, even given the volume of water and the amount of activity, most of the analysis from there are pretty low concentration, pretty low value. But a lot more water. I want to kind of show that slide, but the paper, the Journal of Geochemical Exploration, if you're interested, the articles out there, controls on the lithium content of oilfield waters in Texas and neighboring sites or states. The values on average for the Gulf Coast and the Eagle Ford Trend, both on the northern and the southern side, are relatively low. You see, smack over in Arkansas is put like greater than 100 ppm. Because it's typically, on average, greater than that. In Texas, it's about 152, and that's with the limited samples of about 12 at the time that this spreadsheet was put together. I think that value has increased, quite a bit since then, just because we're finding a lot more high values, or at least a lot more high values are being reported. The Louisiana and Mississippi smackover is historically and typically lower values. Let's see, Anadarko Basin, for example, on average is a very low number, but there are a few samples that are very high, and so we don't quite understand why those values are as high as they are yet. And typically, the Permian Basin is around somewhere between 10 and 30, but 20 on average. So as a snapshot looking at TDS versus lithium on the left-hand side, and the depth of those formations where those analyses were taken from with the lithium compositions or lithium concentrations on the right-hand side. You can see that there are some trends, that some of those formations at depth are pretty consistent, and then some are not consistent at all and have a very wide range of concentrations. Almost all of these charts where the Anadarko Basin is going to be this kind of yellow symbol or yellow diamond, the Eagle Ford and Edwards formations in South Texas is going to be those green triangles. Smackover is kind of divided into the different groupings. In general, Smackover is kind of a purple square. Texas and Louisiana are the kind of red open squares, and then the Smackover Mississippi is kind of a light blue color. So the kind of the dominant feature on depth for the Smackover, you can see how it extends. Both Anadarko, Smackover, and Eagle Ford kind of extend to those higher concentrations. So it really kind of breaks out from the background noise that is all the other samples and all the other basins around the state. So lithium's not rare. It's there, and I guess economically, if we had technology that could economically produce, a lithium product at 20 or 30 ppm, then the Permian Basin would be great because it has lots and lots of water, millions and millions of barrels every day going back downhole as a waste product. So it sorbs to clay and organic material, and so if we lose that clay sorbing capacity, or if the organic material starts to mature, then lithium becomes liberated, and you have a higher lithium concentration there. So on the right-hand side, so this is just the Midland Basin, kind of broken up into Sprayberry and kind of Wolfcamp formations, and you typically have an increase in lithium concentrations with depth. The Delaware Basin is a little bit different. All of the groupings is not really a strong trend, but is typically lower than the Midland Basin and a little bit deeper. So the Eagle Ford and Edwards formations, the Eagle Ford, most of the samples in the Eagle Ford and the shale material is not high, right? Somewhere in the sub-10 range. The Edwards formation, being most of the host rocks, typically being these carbonates for some of these brines. It has a wide variety. You can see there's a lot of promise, I think, probably in Edwards and looking at more analysis out of the Edwards formation. It kind of goes into the lower range of most of the Smackover samples that we're seeing. And there's not been a lot of exploration for this purpose down in South Texas yet. So I can see this becoming kind kind of a stronger exploration area in the near future. The Smackover samples that we have here kind of extend all the way out. It's kind of random. I think we need more samples in order to fill that gap for both Texas and Louisiana. Louisiana in general and Mississippi both have lower concentrations of lithium inside their brines. So really the focus has been on Arkansas and the extension of Arkansas into Texas and the Northeast Texas for high concentrations. Kind of on a log scale for both lithium over TDS and lithium. Just kind of see what that background noise looks like at the lower ppm range, and there really isn't a strong trend other than just slightly increasing with depth for the typical background lithium concentration sample. But you do see the Anadarko Basin, Smackover, and Eagle Ford trends step out from that as high concentrations. So high lithium samples, they do correlate well with high TDS, like I mentioned, as well as boron. You can see that the Smackover in Arkansas, those purple squares, it stands out as those high values of calcium as well as TDS. You can see that there are trends that form where the Anadarko Basin at shallower levels has much lower concentrations. More trends of bromine. Bromine stands out really with the Smackover in Arkansas. It doesn't really stand out in Texas so much, or Louisiana and Mississippi. It seems to be a real Arkansas-focused value. And so you can see that it definitely stands out compared to the either Eagle Ford or the Anadarko basins, as well as all the background noise or the background samples across all the other basins. So I put in the cross sections just to get an idea about kind of where the 10,000 foot level at depth is for comparison of kind of where these samples have been taken from in the different basins, as well as the kind of the cross section back from that earlier picture. One of the focus of this study was to try to figure out where is the lithium coming from? Where is it being sourced from? Both on an exploration scale as well as just as a scientific understanding of how lithium is migrating and where it's coming from, how it's concentrating over time. And there's a lot of speculation on where those potential sources might be. And so we did a little over 100 analysis for lithium isotopes so far and kind of broke those out. If you look at the literature into like saline groundwater or seawater, if the very high value of the delta lithium. Saline groundwater has typically higher values but lower concentrations, and then continental hydrothermal fluids or those continental brines or geothermal fluids. They have continental crust, and then the salar or the playa type deposits with high concentrations but low delta values for lithium. So that plot, I think I covered it up, but the y-axis there is delta lithium, and the x-axis is lithium concentration. So the breakout for the Permian Basin is both the Anadarko Basin is at that shallower level of depth, and it has a very different signature for lithium isotopes than the other groups. The Eagle Ford Formation, for example, has very low lithium content, but it has the signature for the lithium content is very different from that of the Edwards Formation. It typically increases with the Edwards. That's brought out. You can see from the Eagle Ford trend is in those green triangles. It tends to be in the kind of the continental hydrothermal fluid or geothermal fluids. And as it concentrates, as it gets higher lithium values over time, so there's a wide range, but at the similar or same lithium isotope value. So presumably from the similar source, but just concentrated over time. In comparison, Permian Basin is a very low delta lithium signature. Typically, the Midland Basin is a little bit different from the Delaware Basin, but they all have very similar source. That's the presumption is the source is pretty much the same, but just slightly different based on on clay absorption, for example, or organic material that may liberate some of it. And that was the Delaware Midland Basin. You see that the Midland Basin is in blue dots, slightly more shallow, and then you have the Delaware Basin that's in the kind of the open circles that are deeper. Very similar though. So the Anadarko Basin, is very different. It's in the cross section, at least geologically, it's very different from some of the other basins, and especially in South Texas. Much more shallower formation. And those delta lithium values are considerably higher in the 20 plus range typically, putting it in kind of a saline groundwater field compared to the other sources. So correlations, we pretty much decided that it's not, there's no connate or there's no ancient kind of waters that are feeding into these systems. There's association with high permeability intervals. It has to have some kind of communication or transmissivity between the formation and wherever that sourced material is coming from. The host rocks tend to be carbonates, right? And they typically because they have a limited absorption capacity, unlike some of the clays, like the difference between the Eagle Ford and the Eagle Ford shale and the Edwards carbonates. At depth, typically have a presence of major faults that communicate between the basement, but not necessarily sourced from the basement. It doesn't have to be the case for those. So deep formation, no meteoric water input, high total dissolved solids are typical, deep diagenesis, that the high volatiles like boron and potassium or correlation with potassium, calcium, and other salts. And so it just as a source, in general, the saline groundwater for Anadarko Basin, the kind of concentrated hydrothermal fluid or continental hydrothermal fluid and geothermal fluids for the Eagle Ford and Smackover, and then upper continental crust as a source material for the Permian Basin. And if we want to make this economical, we have to improve our technology, take advantage of it. And I think there's a number of projects that are happening currently to develop pilot projects, and there's various, whether it's electrolysis, whether it's there's other methods for capturing that lithium, or if it's some direct lithium extraction technology. There's a wide variety of them that say they're economical, but to date, I don't think we've seen anybody come up with anything commercial yet. But I expect that to happen very soon. We expect it to be in the very near future as those pilot projects. But largely supported by the Department of Energy, and some of these other funding agents will be supporting those projects into fruition here soon. All right. And that's it.
Have any questions for Brent? If you'd go to the microphone for the live stream people, that would be great.
Hello. So this is more on market analysis, not so much on lithium, but when you're looking at how much lithium is going to be needed for the energy industry, has there been any look at what roles like silicon ion batteries or different battery development may change or may decrease the dependency on lithium for battery technology?
Well, I think that could be a factor for sure. I don't think that's as part of the assessment for like the pledge scenarios or the net zero emissions. I don't think that's being factored in necessarily, if that's what you're asking.
Yeah.
I don't think that's being, not on these slides. I don't think the Department of Energy or the Energy Agency is coming up with all of the alternatives that could possibly supplant lithium as a major battery product. Because it's a lot of guesswork, I think, that goes into that. And so I think that you'd have to find something that's going to be definitely achievable and that's going to be realistically produced. And then we have lithium phosphate, we have lithium batteries now as a source. So it's probably the easiest one to analyze that way as far as projecting out need.
Thank you.